And did we return to greatness? Let's make sure. Yes, we are still do not disturb. Fresh here. All right. Cool. That was entirely my fault, guys. So, I'm just going to carry on. What I wanted to talk about today was actually making this Windows thing work. So I started a challenge here. We are on level 1 in practice mode, but I'm going to do something a little bit different. Well, first, I'm going to kind of run through, for those that did not get to see this in class, you can run Windows Connect. This will, in your terminal, this will then drop you into a PowerShell instance that is in your Windows, right? Good stuff right here. Additionally, as the instructions here at the end say, you can go to pwn.college /desktop-win, and this will give us a VNC interface. Now, one of the kind of traps right now about the VNC interface is, even though I started this in practice mode, right now, this VNC user does not have administrator privileges. And a good way to kind of see that, if you don't realize it at first, is if you start something like WinDebug here, you'll see up at the top, it just says WinDebug version 2002.0, right? Now, this is a bug, and it should get fixed at some point. I just don't have an ETA. In the immediate, there is a workaround. If we go start, click up on our username here, we can go to sign out. So we'll sign us out. From there, Windows is going to ask us to hit Control-Alt-Delete, which you can't do on your keyboard over the VNC, as some people have noted. Instead, you go over to this blue tab. You can hit this A character to get access to the characters. You see this little 3-button guy? This is Control-Alt-Delete. And so we can click that and then sign in again. Oh, you did join us. I was wondering... somebody in Twitch here commented that they always prefer in-person office hours. Yeah, but it's good to have you here on Twitch at a minimum. So, and now when I start this, we see it says WinDebug and it has the version, and then it says in parentheses administrator. Now, right now this box is a little bit small. We can fix that. Again, growing pains. Hopefully some of these issues, we laugh at them down the road as we look back at this recording. Right now, we can increase the resolution and then keep changes. And so now I have the opposite problem. My VM window is bigger than my browser window because I'm on a laptop. We can address that with settings, go from remote scaling to local scaling. And so now I have a VNC interface that is workable and usable. Now, you'd have to do that for every challenge, which is why this is an annoyance. But for today, I'm going to do all of my work inside of this one challenge instance, so you won't see me toggling this back and forth again and again. So what I have here, and this is how I kind of like to work with the Windows interface, is I'm in the terminal, and I have a tmux session in Linux. Right? My left-hand side is in Windows, my right-hand side is in Linux. This is important because the way that you interact with these challenges to get the flag is actually from Linux. There's a proxy service running inside of Windows, and you can interact with it with netcat. So if we, from Linux, go netcat localhost on port 4001, we see pwn.college practice, and so we get the flag right there. And that's because the level 1 challenge, the intended challenge, just gives you the flag right off the bat. It's just to make sure that everything is working as intended. But this becomes a bit more of a good workflow when we start thinking about things like pwn tools. Because one thing that we may want to do is write some type of Yeah, good old do.py. It's a file I'm well known for writing. Well, if we write this and say, well, I want a shebang. Well, no, wait, I'm not in Linux. I can't use a shebang, right? Okay. Well, I could still have a do.py. And then we'd say from pwn import star p equals process. And then I need the challenge. For those that are unaware, the challenge is located in the Y drive. So we can do this PC Y. And we see baby win level 1 right there. So Y, I wonder if that works. It does. Right, and so this is a pretty basic pwn tool script we may want to have. And if I try and run this now from Windows, this is probably not going to work. Right? We see that we have problems. And this is why we have this proxy service running. So you can have a Python code running in Linux and still use the tools and kind of things that you're familiar with. Except now we have to use a remote instead of a process. Right. And so now we see pwn.college practice. And so we are able to still script and kind of use these things over on the right-hand side that we're familiar with. All right. Hopefully that is enough boilerplate. Let's actually talk about something with a little bit of meat to it. Over here, I have let's see, I want to do this one first. A nice, simple C file. Is that hopefully large enough? And all the C file does is we have main, I have my func. My func takes 1, 2, 3, 4, 5, 6, and then it returns. I call my func. My func is just going to compute a sum of all of these arguments and then call printf and show the sum. Pretty basic. Right? Now, one of the things that I talked about in class was that Windows has its own calling convention. Right? And so if we look at MSDN fastcall is the name of the 64-bit calling convention that's used on Windows. It describes this here, and it will say somewhere, actually it is not on the fastcall page, it is on the x64 calling conventions page, but it tells us here that arguments are passed in RCX, DX, R8, R9, and then arguments past that are pushed to the stack. Now it also says in here that there is a shadow region on the stack. And this is like something that we haven't heard of in Linux. Right? Twitch chat says they don't know, they don't know things. And it hurts. It hurts to not know the things. So Windows has its own convention, right? When we think about Linux, we know RDI, RSI, RDX, or CX, R8, or 9, right? We have that kind of instilled in us. And that's not going to be the case here with Windows. So if I have my conventions here, C file, what I'm doing here is I'm kind of prototyping a very simple way of me to, or a simple example that will allow me to see this in action, right? Now, this file is located at home hacker on Linux. On the Windows VM, you can access that as your Z drive. And so this means that I can cat conventions.c and I have access to that same file. Now, in my opinion, it's going to be better if you're going to be working with something in the Windows VM to copy it off of the Z drive. Working directly on the Z drive can work, but it can also cause problems in my experience. Hopefully those are resolved. But if not, like shoot me a DM or ping me on the Discord so that I'm aware that it's still an issue. But I know a week ago it was an issue if you started like moving a bunch of stuff back and forth rapidly, right? Like don't copy gigabytes back and forth to the Z drive. All right, there's some magic happening there. Don't put it under load. You'll crash the VM. So I'm going to, just as a good practice, copy conventions over here to C root. Okay. Now, C is not persistent. So whenever the VM stops, this is going to be gone. Okay. I'm also going to copy this magic file that I have that's called dev ps1. So now I have dev ps1 and I have my C file. Now this, right now, this knowledge is kind of scattered across the Discord. But I can't run GCC and produce a Windows binary. Right? I can't produce a PE directly right now using normal GCC over here in Linux, and I can't run GCC over here in Windows. There are ways to kind of circumvent all of this, but they all have their own edge cases and issues and problems, and so I'm trying to make things as clean as they can be. And so over here in Windows land, the only compiler that you have access to is the Microsoft like standard compiler tools. Now, for the most part, those are meant to be used in an IDE. And if you are a big fan of IDEs, there is Visual Studio, not code, but Visual Studio installed on the Windows VM. I have no idea how well it runs. And that is kind of the de facto way that developers use kind of Windows tooling, right? You set all these things up, you configure it in some window or in some IDE configuration window, and the IDE takes care of it, right? Well, under the hood there, much like in Linux where we have these build systems that call make or some type of build tool that then call GCC or some type of compiler, Microsoft has their own build tool. There's mmake, there's msbuild, if I remember right, is the standardized one. And then they have their own compiler. And their own compiler is named CL. We have a problem. If I run CL in Windows, it's not there. And that's because in Windows, by default, that compiler is not exposed to you on the terminal. Now, if I look here in the Start menu, we see that I have Developer PowerShell for VS 2022, right? And Developer Command Prompt. These aren't running as administrator or running with some extra privileges. Well, what's happening under the hood here, the difference between this PowerShell and this PowerShell right now is just whether or not a configuration script or setup kind of file started along with PowerShell here. And so I don't have CL here. This is the little setup script, so that's a good sign. Now I have CL. Now this is super tiny. Not sure if I can make that larger for you or not. No dice there. But hopefully you can see it says usage CL options. I'm now getting an error message from the compiler itself. Well, that's kind of lame, right? Now I have to have this like special PowerShell that I need to start on. But much like, all of our experienced hackers, we know there's something else going on under the hood. And so my little dev ps1 here, this isn't the only way to do it. But this is a PowerShell script that runs this batch file that is buried deep inside of Visual Studio Code. Right? And if you Google this problem, I'll post this on the Discord after if you want it. Don't try and like snag it right now. I think it's already on there actually, but I'll make it more accessible or more prevalent. What this is doing is this is calling that batch file in the terminal and then exporting all of the environment variables. And so this function up here will execute a command and then grab all of the environment variables. And we know what those are from Linux, right? Environment variables exist in Windows. And then it grabs all the environment variables that this batch file creates and then puts them in my current working terminal. It exports them out to it. And you'll notice that I'm specifying here AMD64. It turns out you can run this batch file with different arguments for different architectures. If I were to put AMD64, I don't remember if it's underscore dash, but x86, all of a sudden CL would build 32-bit binaries. Not because I pass an argument to CL, but because the environment is configured differently. Right? So when we think about the GCC as a compiler, we pass some argument to it, and that's what decides a lot of the flags. Microsoft's development environment is a little bit different, or their build stack, where this kind of environment influences a lot of things. So if I run, we saw I don't have CL here. If I run dev ps1, it'll take a moment here, but once it returns, I'm doing that same setup that is occurring when I start this developer PowerShell, right? I'm running that same script, I'm getting my environment configured, and now, maybe, I have the CL command. Now, what's cool about that is it's kind of like this mystery thing that you have to run within Windows. But since we have experience with Linux and kind of a deeper understanding of how some of these mechanisms work in general, we can reason about what is going on that's causing this to occur. Like, why do you think CL is suddenly here? What changed? Like, how would I make a command accessible on Linux? What environment variable would I influence? Path. You know, what are the things that changed when we ran that script?
Whatever the Windows equivalent of path is.
Yes, the Windows equivalent of path, which is path, got updated, so now it has access to that command. Right? And so there are a lot of equivalencies here. I'm going to run the CL command, 365,
Yes.
downstairs, hang a right. I'm going to run the Microsoft compiler, and I'm going to give it the /zi argument. On Windows, some arguments are dash, like you see on Linux. Others are whatever this slash is. I don't know if it's the forward one or the back one, but the normal one that we use in Linux can be used in some contexts as a flag for passing arguments. /zi is I want debug information. Right? This is how I'm getting you guys the PDB files that are apparently not always correct. Okay, so I have this, what did I call this? Conventions.c. We run that, and I think this is important to show so that way if there's something that you want to test, you can do the same thing. You can write your own C files, you can play around with things that you read and experiment. Twitch chat says, isn't it easier to put the path for CL in the Windows environment variable permanently? So when I ran that batch file, it's a good question, and I had the same thought. I haven't tried it, but I'm just thinking here like to myself. Does it take that long to set an environment, like a single environment variable or update the path? No. CL is one binary. I just said that depending upon what argument we gave to that batch file, sometimes it'll make 32-bit binaries, sometimes it'll make 64-bit binaries. I haven't looked at the batch file and see what it does, but I imagine there's a bit more to it than just updating the path. Right? There's other things that are being set and configured that I am just not personally aware of. But I'm sure we could do some type of equivalency if we really wanted to. So it's a fair question. Okay, so I ran my compiler here, and it says out conventions.exe /debug conventions.obj, and I should now have two key files. These are my output, the executable file and then the PDB file. So in Linux, we typically think of binaries as having the symbols compiled inside of it, right? There's debug symbols, there's the kind of the default symbols, and then there's strict, where it just has nothing. Windows takes a different approach. By default, there's just no symbols embedded in the executable. Instead, all of the symbols are in this PDB file. This is interpreted by the debugger to then inform the debugger of where symbols are and how to resolve them. Okay, so if I run my conventions exe, it just tells me the sum is 21. That's not particularly exciting. Right? So let's use our debugger. Oh, I had one. Do I have two now? I do have two. I only need one. Now this is where the show starts. So I'm going to launch an executable. And what I'm looking for here is going to be C conventions exe. Okay. And so it started right here, and it's launched, kind of a command terminal that currently doesn't have anything going on. And that's because, as all good debuggers should, it has paused. This one I know I can make larger. See if I can find the right buttons to hit to do it. Because I know this is pretty tiny on the screen. There we go. For those that want to do the same, you click up in this window, and then it's Control plus or Control equals. Okay, hopefully that is large enough. And what we see here is our WinDebug has loaded this conventions file, and it tells us a few things. It tells us mod load conventions exe. We see ntdll. We see this kernel 32 DLL. We see kernel base, and it gives us address ranges for where these are where these images are located in memory. Now we can see the same thing with LM, which is shorthand for list module. Except now we see a little bit more information. On the right-hand side, we see conventions.c has private PDB symbols, and it shows the path. So the debugger picked up our symbols file because it was located right next to the executable. And that's why it says, hey, we have them. Kernel base, kernel 32, they say defer. Means that the debugger thinks it can get symbols, but it doesn't have them right now. And then we have ntdll, which says PDB symbols, which means it has those symbols. What does it mean to have symbols? Well, it means I can reference the kind of names that are notated, right? So we can look at the symbols that are located in conventions, in the conventions module, with the X command. So I'm going to X conventions, an exclamation point, because I'm referencing something inside of this module, and I'm going to look for main. And we can see now that there is an address that corresponds to main. This command also accepts wildcards. So if you wanted to see like everything that's inside of main, there's a lot of stuff. A lot of stuff. Right? Did I write a very big C file? No. But there's still a lot of symbols here that can be referenced. So the symbols file is definitely useful. Now, what I wanted to do was, if I go back to my C code that I wrote, we'll go poke at it here in Vim. So I wanted to see how does this myfunc get called. Right? I want to see this calling convention thing happen. So one thing that I may want to do is, and we're still broken like before we've gone into main. And I know that because if I hit K, which is the equivalent of backtrace or BT, I can see the call stack. Right now, we are still all the way up here in ntdll. We're still in the loader, right? We're in the loader initialize process. Very much like what we see in Linux, there is a loader that has to bring all this stuff into memory. And so we haven't even gotten to main yet. Or we can set a breakpoint at main. In my opinion, others will probably disagree, and they may be correct. If you want to set a breakpoint, BU is probably the breakpoint that you want. There's a number of breakpoint commands. There's BP, BU, BM. BP is for an address. It is assuming that the address is resolved. BU is break unresolved. But if I give it something that is resolved, it's still happy. So in my experience, BU is probably what you're after. So I want to set a breakpoint at main. Based on what you've seen, how do you think I do that? Any takers?
Just main.
Just main?
Yeah.
I think that'll work, actually. Okay, so it didn't yell.
Is this because we have like debug symbols and all that stuff?
So the question here from Twitch, or not Twitch, from not Twitch, in person, did this work? Was I able to BU main because I had the symbols, right? Because I had that PDB file. The answer is yes, but no, but kind of. Okay. So it's a little bit deeper than that, right? The main got resolved because there was a symbols file. That is correct. Now, the implicit thing that I was kind of going for here, that I think was deliberately trolled, which is fine because it brings up an interesting point, right? Was what I was kind of expecting was this same notation that you saw, right? Where I have the module name, exclamation point, followed by the symbol. Now, if I had another module loaded in here that had a main function, that BU main would not be a happy command because it wouldn't be clear which main I wanted. So a good habit is to specify the module as well as the symbol when you're trying to reference breakpoint or a location or something like that. But in the event that the symbol is unique, yes, you can just break it main. I can list my breakpoints here with BL. Now, if I want to continue, in GDB, we typically use like C, right, for continue. In WinDebug, the mnemonic here is go. And so the correct character is G. We're going to go. Now we see, oh, that was super convenient. It also saw that I had the source file in there. I didn't expect that to happen. It happens to be on the same path, so it pulled it up. We're going to just pretend the source doesn't exist for debugging purposes. We have it over here in Vim, right? That's way better anyways. So now I'm here at main. Right? Well, I may want to look at the assembly instructions. We can do that. We would think from GDB we want to like disassemble, right? Disassemble. But that command is not going to work because the mnemonic for WinDebug is unassemble. So it's U, and then you would provide the location that you want, which right now I'm interested in RIP. All right? You'll notice that I reference the register with an at. That is, we can think of that loosely. It is definitely not the same thing, because there's a deep rabbit hole here that I'm trying to avoid. All right? We can think of that roughly the same as the $sign or like $RIP over in GDB. And so now we see some assembly instructions. But what if I want to see more of this, right? Because I want to really see where this call happens. Well, we can disassemble the whole function with UF for unassemble function. And this is actually pretty useful command. And so now I get the whole thing. We see that it's really not that big, right? But by default, it didn't output the whole thing. So let's take a quick look here and see what is happening. Now remember, in our main file here, we just passed the arguments 1, 2, 3, 4, 5, 6. So we should be able to identify where these values are being placed. Now, per the calling convention, the first argument is placed in RCX. And we see move one ECX. This is functionally equivalent to move one RCX, as hopefully we're aware. So that makes sense. Then we have EDX, makes sense. We're moving 2 into EDX, and we're just looking from when this call, when my func is called, and looking back up. How is it setting up these arguments? So we see RCX, RDX, R8, R9, RSP plus 20. That's a little bit weird. Why plus 20?
Because the convention is to reserve some spaces for the non-stack inputs.
Okay, so the comment here was it is because the convention says that we're going to like reserve space for the non-stack arguments. Right? We essentially make space as if we were pushing these values to the stack. And so the spec says that the call E, so in this case, my func, has the expectation that it has hex 20. So what's that, 32 bytes?
Yes.
It has 32 bytes up there to play around with and do whatever it wants. Typically, or like, no, I would say typically, there were a few reasons for this. One, at one point, arguments were just like pushed to the stack. Two, as far as fast call goes, it can be used for debugging purposes, was a thought there. So instead of having the values hiding in registers, in debug mode, these values could be placed on the stack. So then if I break at something, I can look right at the stack and see what the arguments are. Okay, that makes some sense. But in practice, it's the rule. Right? And there actually is no guarantee what the callee will do with that space. The callee just knows that I have it. So if I don't make space, which, if we go a little bit further here, there's sub RSP hex 38. That is making the space so that when we call my func, because my func's just going to assume, hey, I've got 20 bytes up here, or hex 20 bytes, right? If we don't make space on the stack, for the callee will just mess up whatever we have going on up here. And so it's very important that the caller make sure that there is space for the callee to interact with.
For functions that don't have 4 arguments, do we still reserve hex 20 space on the stack?
Once we finish this, let's change the code and see. Right? Like that. I think I know the answer, but I don't want to just like blurt out something I'm not sure of. So we'll find out together. Like I'm pretty confident of my answer, but it could be wrong because I haven't seen it myself. Like I haven't looked at it and been like, clearly this is the answer, right? And I think that's a good mentality to have in general. Right? It's okay to not know stuff, right? As long as you have some way to like figure it out or reason your way through it. Okay, so we get what's going on there. I think. We have the minus hex 38 because it's hex 20 for the shadow space. Then I have another, it's interesting, those are both D words, but they're pushing them at a distance of quad words, right? Because the arguments are expected to be quad words or 8 bytes in size. And so we have space there, and I don't know what the last 8 is actually being used for, to be honest. Because the act of calling should push. Oh, actually, yeah, I'm not going to say that. I'm not sure why there's another 8. Okay. So what if I want to continue execution down here to conventions? Well, I could set a breakpoint, right? We might even be able to BU conventions, or my func, right? It might be the only my func there. But we can do something else. So in GDB, we typically think about stepping, right? And we single step. Let me see, what do you got over here? Dark magics. All right, Twitch. Well, what do you got? Something of realizing source code is in the same directory. Yeah. Giving context for my comments. Yeah. You're a decent troll, right? Sometimes it's educational. So Twitch says, doesn't it need to be aligned by 16-bit? And this is in response to why is this hex 38? So that is my suspicion. So one of the rules of the fast calling convention is that the stack pointer does need to be aligned by 16 bits, except for in the epilogue and prologue, if I remember right? Which means or implies that we could have this be minus hex 30, and then the callee could fix it up on their side. Like, it's unclear from what I've seen on the spec. Yeah, right. The spec does say that RSP should be aligned by 16 bytes, but it says except for, let me find it, prologue. Like, it specifically says, maybe it's in the fast call page. Prologue. Okay, I'm not going to waste too much time there. But I know that I've read in the prologue and epilogue is when that is not necessarily true. And so it's unclear from the spec itself if that is immediately at the time of call. Right? And the reason that you would need it to be 38 here, or hex 38 at the time of call to make it stack aligned, you'd be like, but Robert, hex 38 is not 16 byte aligned. You'd be correct. Right? But what does call do as an instruction? It pushes the saved return address onto the stack. So minus hex 38, then we push an address. That would get us minus hex 40 for the total stack, which is an offset that is, in fact, a multiple of 16. Yeah. I'm not entirely sure that was the, I think I know why it's doing that, but I didn't want to, concretely say this is why. Okay, so we think of stepping. Now, in GDB, we step with SI. In Win debug, we step with T. So, and it's the mnemonic here is trace. So we're going to be tracing. Oh, it's going to just keep showing me source because it wants to be helpful. Thank you. And so we're stepping into this function, right? Now I could just step my way until I see that particular line that I'm interested in, the call instruction. But there is a pretty handy thing that there is no, as far as I'm aware of, similar command in GDB, and that's TC. This is trace until call. And so I don't have to know what the call instruction is. It's just run until something gets called. And that's actually pretty handy, because how do we typically think about assembly when we look at it? It's here's the function that's being called, we look up and find what are the arguments, right? Or we find the syscall, we look up and see what's going on. We find the thing in libc, we look up, and okay, this is what's happening. And so what's the next thing that's interesting here with TC? Well, the next thing that's interesting, the next call, is the call to myfunc. Now, if I were to hit P for step, this would step over the call, which is not what we want. If I hit T for trace, then I'm going to be tracing this call. I'm tracing the function. So I'm going to step inside oh, this is printf. You want to go inside printf?
Sure.
I don't know what's inside printf. Okay. So we are now inside printf. Yes. And so this is going to jump. And then it's going to jump again, if I remember right. That is the source. Well, it's the header file. So we haven't gone deeper. Man, WinDebug is all over it. So one of the things that probably happened. Yes. Along the way here, if you'll recall, kernel 32 was deferred as a module. But now it says PDB symbols. The symbols data for a lot of the Windows things are not actually saved on your system. They're saved on a Windows symbol server. And fortunately now, it wasn't the case at launch. Fortunately now, the Windows VM can go out and grab that symbol data. So hopefully that makes things less painful for you as you're debugging here. And so that's how we saw this stuff get updated. Now, I do not actually want to go into printf. I want to go up. I want to escape. I want to finish. In GDB, it would be finish. In WinDebug, the mnemonic is go up. So it's GU. All right. Now, I can look at my stack trace here with K to see where I'm going to go to. So right now, I'm here at conventions printf. I want to go up one and return to my func. And apparently that was a mistake. I did not want to do that. Okay, it was just running and taking its sweet time, I guess. I think that's the cost of like going out and getting symbols and showing me all this source, all of these niceties that we don't need, right? I want to go back to my terminal, all right? For the record, there is a terminal version that is just this command window of WinDebug. I just don't have it configured yet on the VM. Once I do, that is all you'll see from me doing with this. It's called CBD, or CDB, I'm sorry, CDB. Is the userland terminal debugger, which is what is running here underneath WinDebug. Okay, so I'm back here in my func. I need to know where I am, so let's unassemble at rip. Oh no. Yeah, no, I'm good. I'm in my func. Let's unassemble my func. I think I skipped what I was really after. Oops, it's not you. It's UF. Bam. Okay. There's quite a bit going in here, but this is really just all addition, right? But we see something interesting. The callee is subtracting from RSP-X38. So the caller made the space, and it's the callee's job. If we go back up, hopefully it's not too far. It is too far. All right. Let's look at conventions main. We made the space as a caller. The callee then cleaned up that space. And so we assume that the callee cleaned it up. We don't have to clean it back up afterwards. And so that is the calling convention, right? And we see here, it does the subtraction, and then it starts referencing things relative to RSP. And what do we see is going on with kind of that shadow space? Well, it's doing that exact thing there. It's putting ECX or RCX onto the stack. It's putting EDX onto the stack. It's putting R8 and R9 onto the stack inside of that function. It's doing that debug behavior that I just said, hey, maybe the function does it, maybe it doesn't. And so that is how this function decided to use that scratch space. Now, why it decides to subtract this early and then do new math is, that is a design decision all on its own. But that is what we see here. So hopefully that makes some sense, or helps you think about how this calling convention works, or how fast call works. Any questions about fast call while I'm here? No? Okay. You will need it for the challenges. All right. Hopefully that is a sufficient understanding. Q for quit. That one never changes. All right. Well, that's not true. No, Vim is Q. What's Emacs?
I don't know, Control X, Control C or something.
Okay, yeah, Emacs breaks it. Yeah. So somebody has to have a mnemonic that isn't consistent. Okay, now let's do something a little bit different. Let's open the challenge from level 1 that is supposed to be ran in this. Baby win level 1. Hopefully it doesn't show the source on this. So we are here, and if we list our modules, we have Baby Win level 1, and it says we do have symbols, which is a good thing. There should be a main function here. There is. Let's dump out the assembly for it, or unassemble it as a function. That calls win. So now I want to look at win. I'm looking for something in particular here. Okay. So it has produced quite a bit of assembly, and it's notating it a little strange here in sections. Well, what I'm looking for is where this is written out. Now, printf is a perfectly good function. However, in these challenges right now, because of an edge case, they should not be using printf. Instead, we are using the functions create file, which is the equivalent of open on Linux. We should be using read file, which is the equivalent of read, and we should be using write file, which is the equivalent of write. Now, you'd think, well, open, read, and write, those are Syscalls, right? That makes sense. So there's got to be Syscalls in Windows, and there are, in fact, Syscalls. However, if we were to look at MSDN create file, I'm going to go with create file A. This is not a Syscall. This function is part of the Win32 API. Somebody has the answer. I don't have that problem anymore. I appreciate you finding the answer to make the source not reappear. There's something I can untick up at the top. But I have successfully avoided that problem at this point, or escaped it. So we have create file A, and it is part of the Win32 API. In Windows, you don't call Syscalls directly. But if you think about what really happens in a normal Linux program, do normal Linux programs call Syscalls directly? No. What do they use?
Probably wrappers and stuff.
Right. There's some type of wrapper, right? Like if I want to call open and I'm writing something in C, I import. Actually, I don't know which header file it is for open. Read, I believe, is uni.std.h, right? So the Unix standard header file. Right? And so that header file determines what actually gets executed. And so there's some wrapper around that is going to like sanity check and provide errors in user land before just calling the syscall and going right into the kernel. Right? libc is going to try and protect us from ourselves. And that is a good thing in general. Well, that same logic exists here in Windows. Right? We don't want to call syscalls directly. Instead, we have the Win32 API, which is the variety of functions that we want to interact with. But if you've taken 466 or gone through the system security content, you know that you can call syscalls in Linux. Oh no. GitHub. Yes. No. GitHub. Windows. Syscall. This is what I'm looking for. Juru Windows Syscall. All right. So when we talk about Linux, we like our buddy Ryan A. Chapman, right? None of us have met the man, but he is a legend. All right. He is a legend for providing this amazing document here that has stood the test of time. But it's not that one. It's this one. No. But it tells us what value should go into RAX when we trigger a syscall, and then what are these registers used for to trigger the syscall. And we can use this information to write shellcode that just performs a syscall, right? If we get 0 into RAX, we set up these 3 registers and we execute a syscall, boom, sysread happened. That's pretty awesome. And Ryan H. Chapman hasn't had to update this document in quite a while. And that's because Linux has a stable ABI. The interface between the kernel and userland is documented and doesn't change. Well, it does change, but it doesn't change in breaking ways, right? They have actually invented new syscalls over the years. That's why we have, I think we're on like clone 3. Right? There was an original clone, and we've since reinvented it twice since. Right? But if we look here in the syscall table, there's sysclone. Well, that's 56, and it still behaves like it should. I guess clone 2 and clone 3 have been moved. They are just wrappers. I thought clone 2 was a syscall. Rabbit hole. Okay, so I guess that's a libc implementation then. The libc is handling the clone 2, clone 3. Bummer. But the point is that they do create new syscalls. But generally speaking, we see these all go in order. So where do you think the new ones go? They go over here on the end, right? And as the kernel gets updated, we just say, what's the next number? Cool. This is the new code for that syscall. Now, not even Windows can stop me from looking at man pages. You are correct, sir. Okay, man pages are great. So we have this kind of stable setup, right? And we notice that this makes sense. Over time, we just increment this number and things are good. Windows has a slightly different approach, right? So Linux is open source, which means a lot of people interface with the kernel, and there's a lot of interested parties that may use the information of the entire open source Linux kernel for whatever purposes. And so it's important to the Linux kernel that this information is stable. Windows, on the other hand, isn't kind of constrained to this. The only people that Windows cares about, right, is Windows. Nobody else is running the NT kernel, which is the name of the kernel for modern Windows, if you were unaware. The only thing that has to interact with the NT kernel is Windows userland. So that means they're free to add syscalls, remove syscalls, and even change the syscall numbers that are used. This table here this is the NT write file, is the syscall kind of level wrapper function of what we are doing over here. Where we are calling write file, we are calling, why did I go create file? Let's do write file, msdn write file. Okay. So we in userland call write file, which is part of the Win32 API. The Win32 API is going to do whatever it wants to translate its way down until it gets to NT write file. This is the syscall layer that communicates between userland and the kernel. And if we look at this number, we're like, Robert, what are you talking about? The answer is 5. It's clearly 5.
Until it isn't.
And then, wait a minute, it's 6 in Windows 8. And then in 8.1, it's 7. And then it's 8 at Windows 10. Right? And so these numbers actually change. It isn't consistent and stable. It isn't just a monotonically increasing number as new syscalls are released. And we see that it's not even like it's just Windows 8 versus Windows 10 where this number is different. Here, these are both Windows 8. It just has a different update package to it. Or with Windows 7, there could be something that's different between Service Pack 0 and Service Pack 1. And so we don't have that guarantee when we're writing code for Windows that any given number is going to correspond to a specific syscall. Now, I said this is NT write file, and this is a syscall. What happens if I go msdn nt write file? This will exist. And so now you'd be like, well, Robert, we have write file at home. We have write file right here. We have it in the Win32 API. Why do I need write file again over here with this NT write file? Right? This is just silly. Well, it turns out there's write file for thee and write file for me. Okay? Userland should use write file from the Windows 32 API. This is the interface that all userland processes use for write file. And it looks like a pretty sane looking interface here. I have a handle, which if you're unaware is very similar to like a file descriptor. So I have a handle to a file. Okay, got a pointer to a buffer. This makes sense. This looks just like write so far. I have the number of bytes I want to write. That makes sense. I have this. This is a little bit different than what we've seen in Linux. We have number of bytes written. Well, when we call write in Linux, we think of the return value. In Windows, you pass it a pointer, and then it places that value at the address that you provide the pointer to. Okay, that's not a big deal. And I failed to mention it, but we have kind of these weird types, right? LPC void, LPD word, right? There is a pattern. These do make sense. They are not nonsense. If you look at MSDN data types, Windows has a convention of kind of type defing things so that they have semantic meaning, right? Everything isn't just a void star. Instead, we have, this is a long pointer to a D word. This is a long pointer to a C void. So this one actually is essentially a void star. But we see that we do treat these differently. And hopefully, if the userland programmers use these type defs, or at least they have to explicitly cast to these type defs, it will cause less problems and less errors in code. All right. And the last thing we have here is this overlap thing, which I'm not going to go into, but if you scroll down, you'll see that it's some type of magic struct that can be used for read-write instances. Some of the arguments are optional. Optional means it can be null. It doesn't mean that we can just exclude the value. But still, this is pretty user-friendly. This is write file for me. Now, write file for Microsoft, on the other hand, has a few more arguments. So, NT write file, all right, takes a handle. So far, so good. We also have an event handle, and we have an APC routine and an APC context and a block thing. And then there's a buffer, all right, and a length, an offset, and a key. I have no idea what most of these things are. Now, this particular syscall is documented, right? And that's because this documentation, if I scroll up over here, okay, no, it's just a documented kernel kernel function. But a lot of the kernel or native layer functions are undocumented, where you can't actually see what this is, right? Or Microsoft at least doesn't officially provide it, because it's not intended to be used by userland. But we see it's a lot more complicated down here. In NT write file, I don't know if it has, but the next time Windows updates, they could change the entire way this works. There's no guarantee that this is a stable and consistent interface. And so this is for Microsoft. and it's not for the userland. But this still does get called, nt write file. If I go back to good old WinDebug here, we see that impl write file is getting called in this thing. Now, write file calls the implementation of write file, but I'm a believer, as you know, often falsely believing. We have a number of modules here. We said we have kernel base, kernel 32, and NT-DLL. We've seen these last time. We'll see these almost every time in every binary because they are all involved in kind of using that Win32 API. The layer that is the Win32 API is kernel 32. So if we look in the kernel 32 module, there should be write file, and there is. But I believe there is also, inside NT-DLL, NT write file. I'm going to set a breakpoint here at NT write file. Okay, fire off, breakpoint 0 hit. So now I am inside, I am at the call to the kernel. Let's take a look at the backtrace here and figure out how did we get here. Well, the loader was somewhere up here, and then it fired off baby win level 1. All right. Right here we get to main called win. Win called what? Write file. And write file we said was in kernel 32. But instead I see kernel base, and then I see NT-DLL. So what happened there? Well, kernel 32 we look at it here, we'll see there's actually not a whole lot going on. Kernel 32 write file just jumps over to that implementation. Then if we look at that implementation, oops, that is not what I want, actually. Because if we look at the assembly instruction, it is jumping to the keyword that is pointed at this, which means I actually want the symbol that is located at this address not to unassemble this address. Yeah? Okay, that one may have been a little bit too fast. Okay. If I want to examine a symbol, in GDB we do like x/g and then an address, right? For examine a giant at some location. In WinDebug, what I want is D for display. DQ, I want to display a quad word. Where do I want to display it? I want to display it right here. Now, WinDebug by default is going to be like, here's some. You don't get 1, you get, I don't know, 20, right? Whatever Windows thinks is a good number of them. So there you go. There's a whole bunch of D words. But what if I only, or Q words, I'm sorry. What if I only wanted 1? There's a general convention for specifying ranges or quantities where at the end here, or within your range, you have the address space L and then a number, and that is the number of things that I want. So if I do that same thing but append L1, I'm saying, give me just one of these. So, assuming I parsed this assembly correctly, this should be where we're headed. And if we unassemble right there, we are now in kernel base write file. Now, kernel base, we could dig down to this whole thing and see what it does, but that's going to be quite a mess. It is handling the translation between write file for me and write file for the kernel. It's doing that work. So whatever translation needs to happen between the userland API and what the kernel really wants is being handled here in kernel base. It's not always handled in kernel base. Random factoid, depends on the function. But in this case, it is. And where this ends up, as we saw, is at ntdll write file. Okay, well, let's take a look at that guy. Unassemble the function at ntdll write file. Well, this ntdll write file, as we see, is actually an extremely simple function. It moves RCX into R10. For those that remember learning the difference between Syscall calling conventions and function calling conventions, you may have seen this before. Same problem happens in Linux. As part of the Syscall instruction, which we see is happening right here, RCX gets overwritten. That's why when you have big functions, I think the one in 466 you have to deal with is like mmap. I don't remember what the first one you do is, but when you get a function that's long enough to where calling convention says the argument should be in RCX, if it's a syscall, it actually goes in R10. And the reason for that is because when a syscall instruction occurs, RCX is used in that transition from user land to the kernel. And so the calling convention changes. And so what NT write file is doing is it's moving that value from RCX to R10. Because, yeah, if this was a normal function, it'd be RCX, but we're about to do a syscall. So it's just, all right, we're going to copy that there. That makes sense. We're going to move 8 into EAX. Any takers on why we're putting 8 into EAX? I spoiled it earlier. What's that?
Is it Syscall number?
It's a syscall number, yeah. That's exactly what it is. In fact, I don't know if I scrolled my way all the way over there. I didn't. So this particular Windows VM, we got to keep cruising a bit, is Windows Server 2022, if I remember right. So NT write file is 8. And it turns out the syscall instruction still works like the syscall instruction. So yeah, the syscall number goes in RAX, right? So there are things that we've seen in Linux. Yeah, it works the same way in Windows, except not really, right? Because we had like all of this kind of song and dance to get there. But we can make sense of what we're looking at here. Now, this check right here, I wouldn't expect you to know. So I'll tell you what's going on, right? Because like there's no context immediately, right? But it's testing some value to see if it's 1. And then if it's not equal, we are jumping to right here, to plus 15. We're just going to call int EH, then return. But if it is equal, then we're going to call syscall ret. You may not have encountered this in 466, but, oh no, you had to in sandboxing. Different interrupt, different number, but 32-bit syscalls don't use the syscall instruction. On Linux, they are in 80. You want to guess what they are on Windows 32-bit? In 2E. So this is a check for, are we making a 32-bit? Is this a 32-bit guy? Am I going into the kernel from a 32-bit context or from a 64-bit context? If it's a 64-bit context, I want to do this syscall and go into it this way. If it's a 32-bit context, then I want to do this int2e, and that's how I want to jump into the kernel, because the mechanism for doing so is different. Twitch chat says, it sounds painful to use the NT API instead of Win32. So I'm trying to make a challenge that forces you to. I haven't found a way to ensure that you use the native API, but if I find a way, I am going to write a challenge that makes you do it. Because it can be done, right? It's just, and I want you to do it in shellcode for the record, right? It absolutely can be done. And it is something from an exploitation perspective that has actual value. We're not going to get into it today, but there are reasons why you may want to call a higher layer function like the Win32 API versus a lower layer function like the native layer wrapper there. But we saw what the native layer wrapper is doing. Like, it could be write shellcode that just does that, maybe, right? But what happens if I just set this up and trick call Syscall? That could be fun. Okay, so hopefully we see a little bit how this kind of interrelates. Right? Now, what do you think happens if I'm writing, and I don't expect you guys to know C++, all right? But in C++, there is I'm going to say chevron, right? It's like a greater than, and a less than symbol. It's all you need to know. Okay? And what that does is that writes or reads. Okay? So in the C++ runtime, if I use this chevron, what do you think happens?
Probably like calling write file.
Which one? Which write file? We got more than one. Do you think it calls the Syscall itself in the C runtime?
It probably calls a lower one.
You think it calls NT write file? Yeah. And that's a perfectly reasonable guess, right? The answer is no. It calls the higher user level one. So like if you call, and I don't have an example of this because I'm trying, at least right now, to not make you guys step through C++ code in a debugger. I think it's something everyone should have to do, but not necessarily while learning a new operating system, right? Or kind of playing around with this. But the answer is, and we would see this with the C runtime even if I called like, let me think of something. Exit? I think exit C runtime. Let's see if I can do that. Quick detour. Do.c, no, vim do2.c. What do I need for exit? What is the simplest thing I can do? Int main, exit 12. And then for giggles, let's include windows.h. I have no idea if that will compile. All right, CLZI. Let's go to my Z drive. CLZI do2.c. I got to do 2exe. Let's rock and roll. Let's see what happens here. I'm going to do exactly what I told you not to do. An interface with something on the Z drive. Okay. This should be a very simple function, right? And there should be a main. It's LM, so I'm listing my modules. My do2 does have symbols. That's because I did the, again, /ZI, so a PDB file was generated there. How do I disassemble main? What is it? UF main. Cool. That works. Now, this is in the C runtime, and we're calling do2 something that is exit. Oh, what is it that this calls? MSDN NT terminate, I think. Is it this one? I think this is what gets called under all of this calls. This is what I get from going off the rails. I knew what I wanted to do, but I don't want to step through this for the next like 20 minutes. Oh, wait. Okay. Let's see if we can do TC, and then we step in. And we TC, and we step in. It's TC. I like this.
Oh, we're doing a lot of code selection business. Oh.
Okay. I don't believe you're the answer. Set event. We haven't even gotten to main yet. All right. Let's break it main. And let's go rock and roll. All right, let's step. Oh no, my camera has decided once again to not watch me. You saw I was just typing. Okay. Oh, it can't be done. Okay, I can make it be fixed right here so you can get a little bit of it. Okay, so now I'm inside main. We'll unassemble where we're at. I want to get to this call to exit. So TC, we're at the call to exit. Now, okay, now we're going down the rabbit hole that we want. Otherwise, it would have been quite the journey from start to finish, I'm sure. All right, T, unassemble. Where am I? I'm in common exit. Yeah, you noticed that. I didn't. I'm just going to keep mashing T. Okay, now I'm in kernel 32. Get module handle. So I said that a handle is kind of like a file descriptor.
Right. They can use it for a bunch of
Right, but it can be for a bunch of different resources. It doesn't have to be a file. So in this case, we're getting a handle for a module. Right? Now it's checking if it's a managed app, common exit, some type of virtual function, awesomeness, more critical sections. I am almost sure it's like NT terminate process or something like that. But the point is that the C runtime, when you just call exit like that, will call like exit or process exit, or it'll call something in the, I can't remember what it is right now, in the Win32 API. And then that will then again bounce around to kernel base to the NT, the native layer equivalent, to then trigger the Syscall. And so it doesn't even matter if you're writing C code. It goes through even more translations before it calls the Win32 API, before it calls the native layer. Because no one is allowed to use the native layer. All right? That is for me, not for thee.
that allows them to change it out whatever they want, I guess.
Exactly. That's why they can change it out, right? So like in Linux, if we wanted to change the way write works, right? We had some like super awesome new way of doing I/O. Can we just change write? How many things would break?
The world would go on fire.
Exactly. Like literally nothing in like computer science would work. But Windows, because they have all of those translation layers between what everyone gets to play with and then how they route and translate in their kind of internal representation, because they have that clear division, it allows them to update stuff and change stuff under the hood and have it functionally be invisible to the programmer or whoever it is that's working in code up in the user. And so there absolutely is a benefit to this. Okay? But it's definitely different than what we've seen. So if I were writing shellcode for like, I don't know, some course challenge, right? And I needed to call a function. I needed to call like open, read, and write. Okay? Do you think I want to do it at the native layer? You think I want to do raw syscalls in my assembly? Probably not. Like, I'm not saying that you won't pull it off, right?
Unless you know your target.
Unless you know your target?
Or like, unless you know like the thing, like the OS you're running on, like what version.
Okay, so the comment was, unless I know the OS I'm running on. But yeah, it would be not impossible, but there'd be a lot of guesswork involved if I didn't know the OS I'm running on, right? And when you talk about kind of more broadly malware or something that is just going to attack Windows, that is a problem that malware has to solve, right? Well, what syscall number do I need? Well, I don't know. What Windows am I running? Well, I don't know. How do I figure that out? Like there's a whole chicken and the egg problem that exists within that. I don't think that was an intentional design decision on Windows' part, but it is in effect. Somebody says security through obscurity. So I wouldn't say it's intentionally security through obscurity, right? It's at least for this like Syscall implementation. I think of it more like a Bob Ross happy accident kind of scenario, right? In the end, if you can repeatedly, guess, you'll eventually guess right. There's some number of permutations. We see that whether officially documented or not, there definitely are public archives of this type of information, right? So, like, I don't see 128 as an argument just quickly scrolling through this right here for NT accept connect port. So if I was trying to call that, I wouldn't have to guess that. There's probably only 3 or 4 numbers I'd have to guess to try and trigger that. I'm not saying that that's an effective approach, but like in theory here at a conceptual level, it's not meant to be security through obscurity. It just happens to be the way things went. Okay, so that was a fun little journey. And so the answer, I don't know if we hit it or not. If I were writing challenges for or writing solutions for a challenge, trying to solve something for like a course, where I was needing to write Windows shellcode, the easiest thing to do is going to be to try and target the Win32 API. Right. Now, I mentioned in class, although I don't think it made it to the stream, these challenges are meant to be pretty easy. Like I'm not doing anything to make things intentionally convoluted or bloated. In fact, the early ones are just, hey, here is a leak, right? Here's an address. You just get it for free. But it turns out in, I think, level 6, I stopped giving you stuff.
You start top giving stuff level 6. Level 7, you don't give
Level 7, I just say, figure it out, right? I think that's the...
Wait, is the broken PDB part of it in level 5?
No, that's just moving.
No, that's just, no. If the PDBs are broken, that's entirely on me.
Okay.
Like odds are, that's just me doing something dumb. As a side note, I will probably sometime this weekend regenerate the challenges because these right now, as I mentioned, were like just handwritten by me, which is why like sometimes somebody made the comment, "Oh, this works and prints one way, but if I use the proxy, it doesn't." Like there's some weird edge cases that I didn't standardize things, so I am going to regenerate them because I am working on adapting our kind of challenge templating engine to work with this whole shenanigans. I think I have it working, but that also means I can randomize offsets and values.
Well, that reminded me of something.
Yes.
For level 1, you use the /r. That was annoying.
I used /r.
And you use the /r at the end of the flag.
I used /r.
Oh, you didn't like the challenge.
What is /r?
Return.
Carriage return. What is /n? Okay. Conceptually, do you know the history between newline and carriage return? You know where they come from?
Is it typewriters?
Typewriters. No joke. This goes all the way back to typewriters. So typewriters, a new line is scrolling the paper up a line. The carriage return is, you remember the iconic sound of like slam, bing?
Yeah.
That's a carriage return.
Oh.
Okay.
Nice.
The new line is when the paper scrolls up. And so I'm going lower. The carriage return is when I move in the horizontal direction and return back to the beginning of the page. Right? And so the beginning of the terminal interface was like based on, because the computers originally didn't have a screen, right? They didn't have any of that. Instead, they printed the paper. And that was your screen, was whatever it printed out. And so the very first computers modeled themselves after typewriters. And so there was a specific code for when the paper needed to go up and when the typewriter interface needed to go back to the beginning of the line, which is why you have new line, go up, carriage return, go back. Now, I don't think, add the carriage return. In Linux, we are an evolved people, right? We have moved past the typewriter. and so when we want a new line, and we have the new line character, it implicitly means that we not only are going to the next line on the paper, but it turns out we are also going all the way back to the beginning. Windows keeps that semantic value for their new line. So new lines on Windows, like if you were to open a text file in Notepad, type something, and type something, enter, save it as a text file, and then copy it over to Linux and take a look, you know what you'd find? You'd find new lines and carriage returns, because Windows hangs on to that history. Right? Not saying one is right or wrong, and it's actually a common problem interfacing between Windows and Unix-like systems because of that. The program or kind of slogan for that is DOS to Unix. There's little Linux programs called DOS to Unix, and you can run them on a text file that uses newline carriage return, and it just cuts out all of the carriage returns so that it makes sense in Linux land. And so that's a common conversion problem. Okay, I got sidetracked. Where were we?
We were about to talk about.
You mentioned something that at one point you were just going to stop giving us stuff in levels.
Oh, I stopped giving you stuff.
Yes.
Yes. I stopped printing stuff. Oh, I'm going to standardize things. And when I re-standardize the challenges, the offsets, if you're working on anything, I'll announce it and ping everyone so that hopefully everyone is aware, hey, I've updated the binaries. You will need to recalculate your binaries or your offsets for like overflows and things like that, because I'm going to add some randomization to it. Okay. Yes, that was where I was. And then in level 7, the description here says, now get the flag yourself. That's all you get. There's no leaks. It's get bent, figure it out. Okay? That's a problem, right? Because up until that point, I give you something to work with.
Yep.
Now, I've heard a couple of approaches at this point for it, but I haven't heard anyone do what I actually was hoping you'd do. And that's okay, because I haven't told you about the things you need to know to do the thing I want you to do, right? That's on me. Fortunately, it will be mentioned in greater depth than I have time today. But what we're going to talk about is a crazy thing known as the TEB. The TEB. So if I want to know more about the TEB, what do you think I want to Google? There's a pattern to everything I've typed.
MSDN TEB?
MSDN TEB. Bam. TEB. All right. I'm glad you picked up on it. Right? I've been sneaking it in there. So, the TEB is the thread environment block, or the thread environment structure. Somebody says, why 7 so hard? We're supposed to guess addresses. You are not supposed to guess addresses. You're supposed to have lecture videos made by your instructor that give you useful information to help you solve these things. But instead, I've been spending my time trying to make sure the dojo stays up. So, the TEB has thread-specific information in Windows. This is much like other things, like I mentioned with the native layer, a semi-documented thing. This is a lie. This is not the TEB. Okay? This is what Microsoft tells you is the TEB. Okay? Much like write file isn't necessarily write file, right? It's MT write file, which is something else and has some other translation. There's a lot of this kind of smoke and mirrors and misdirection going on. But it's not on their fault. They're just trying to keep things that you shouldn't mess with away from you. In the primary purpose that we can think of for the tab is thread local storage. Now, this isn't something we looked at in like great depth in Linux, right? But you have the ability to have data that is local to your thread, right? Well, the same thing exists in Windows land. And the way that they deal with that is through this tab structure. Now, the debugger has this nice command, ! tab. It prints out some information. And I think it's actually a little bit more information than that struct had. I don't know, I haven't like compared, but it looks like it. But what if I told you that was also a lie? And the tab has more than this. So, in the interest of time, I'm going to copy from my Z my other piece of code. This is runner.c. It is not particularly fancy. It is the bare minimum that is really needed here to execute shellcode. All right, it's going to have some region of memory. We're going to call virtual protect on it, or we're going to read into it. We're going to call virtual protect, which is the Windows equivalent of changing the, why am I blanking on the Linux call to change permissions for memory?
chmod.
It's not chmod. There's a call to change permissions for page memory in Linux. It's the equivalent of that. We're making it so it's executable, right? Because I didn't want to mess around with disabling NX. On Windows, NX is called DEP.
Data execution prevention or something?
Yes, data execution prevention. And so instead of messing about with that, which from what I could tell was a system level thing that I didn't want to deal with automating within the VM, instead I'm just saying, whatever. I'm just going to make this region where the shellcode is executable. And then we do some illegal casting and just execute this arbitrary buffer, right? Common way of doing just like writing shellcode challenges. Just do something along those lines. And so it will just execute whatever I feed it. Let's compile runner.c. We've got that. And I have, I can't do that from here. Okay. I'm going to do exit quick detour. I need to be in Windows. I need to copy that compiled binary from C, which was runner.exe, back to my home directory. I'm going to copy the runner.pdb back to my home directory on Z. I'm going to exit. I'm going to Windows stop. This will probably make me have to fix the resolution, which I lied. I said I wasn't going to. From here, I'm going to look at the challenge. We're going to sudo rm babywin level1.exe. And we're going to also remove the PDB for that. Bam. Now we will copy runner.exe to challenge. Then we will copy runner.pdb to challenge. And so now challenge has what did I do? RM, challenge, babywin. I think I have too many copies of these things all over my... there we go. So now my challenge directory just has runner.exe and runner.pdb. Okay. And the reason I'm doing that is because the challenge proxy that we have on here, it really doesn't care what executable is over there in the challenge directory. It will just proxy to the first executable that is chilling there. So this is the equivalent of if this runner guy was the challenge. Unfortunately, I do have to stop the VM and then start it back up. No way, that saved my... That's amazing. It remembered my resolution. It didn't remember the VNC though. Or the VNC didn't remember it. All right, I'm in practice mode, but I'm gonna need to do some admin stuff. So again, because the dojo right now is looking for help in Windows, we will log out and log back in. All right. We'll fire up WinDebug again. And so I should be in the administrator group, and this should say administrator up at the top. That's how I know I can be fancy here. Now, if I did everything correct from the Linux box, we now have an ability to interface with that shellcode executor. Right? We see ready to receive shellcode, it reads it, then it runs it. Cool. What I'm going to do, you just have to blindly believe me when I say this, but this is a convention. Thread local storage related things, there's two segment registers. I'm not going to go into the history of segment registers because that would take like 30 minutes. All right? They're a historical artifact. The only two that are really used in a serious manner nowadays, although I'm sure someone can correct me, is FS and GS. You've probably seen these before. We saw them with the canary, right? There was just this like GS thing, and some offset of GS is where the canary came from. Well, you know what the canary is saved in? The thread local storage. So that GS that's being accessed is accessing the canary from a thread local context that is accessible from this magic segment value. The similar thing exists in Windows. So if I do context arch AMD64 A equals ASM int3, because int3 still works, I'm going to move RAX, and I want GS offset by 0. I want the value that is located there. And we have R equals remote, localhost 4001, R send A, R interactive. I have one problem. We aren't waiting for GDB anymore. I'm sorry, IPython. We're now waiting for WinDBG. We are living in the future. All right, so I've ran this, and my Python code is now blocked on that input, right? So, that actually is not going to do what I want. Bam. I need to make the remote connection before I block. That'll do what I want. Does everyone see what I'm doing? Cool. I'm connecting to the challenge proxy. The challenge proxy will start up this challenge upon connection. The challenge is now blocked on read. That gives me time to attach a debugger to this and see what is really going on. Now, in order to attach, I do have to be, why is this just a little bit too big for me? That makes me sad. I do have to be administrator, which we see up here, up at the top. We also have this option to attach to a process. If I click that, I should be looking for runner.exe. And if I look through this list, we will see that there is, in fact, no runner.exe. However, we look down here at the bottom, it says show processes for all users. And if we click that, there's a whole lot more going on. And if I scroll down a little bit, runner is a bad name for this thing. It's going to be hiding somewhere in here, right there. Now, an interesting thing worth noting is this isn't being ran by hacker. This isn't being ran by administrator. The user that is running this is system. It is NT authority system. That is the equivalent of root on Windows. A lot of people think, hey, admin privileges are root. It's not. It's this system guy. And so this is that challenge. And if we double click on that, we have now attached to this runner exe. All right, that's awesome. Let's hit K so that we can look at our backtrace. Does this make sense for what I just said? I said that the challenge should be blocked on read. Why does this say RTL user thread start, base thread init, remote break-in, breakpoint?
Because WinDebug works by spinning up an alternate thread and putting a breakpoint in there, basically.
Right, so this was a bit of a troll question because I said this in class. Because this is a common gotcha. The way WinDebug attaches is by injecting a thread that then triggers a breakpoint. If we look down here in the bottom right, it's going to be very tiny, and I don't think big is an option over there. But we see that there's two items. Right? These are two threads. And so right now we are on the thread that was injected that triggered the breakpoint. To switch to the first, well, to list threads, it's squiggly. All right, we see 0 and 1. I want to go to thread 1, or thread 0. I'm sorry, I'm on thread 1. And then S, so it's thread 0 set, is how to kind of mnemonically remember this. Now, if I look at K, this makes sense. I'm inside of NT read file, which as we now know is the native call that is being called by kernel base, which is then called by main. Hopefully this call stack makes sense, at least the later part of it here, since we didn't get into the init stuff. All right, let's find, do I have symbols? Yes, I do. Let's break at runner fn. Fn doesn't exist. What did I call that? That's a shame. Okay. Let's break at main. All right, that exists. Oh, it doesn't. I shouldn't have done that. Gosh dang it. We got to start all over again. Attach to process. I don't have a process. Finish this guy. Fire him off again. Make sure we check for all users. Find runner. What happened? I tried to break at main, but we're already past main because we were blocked on read. So that was not the move to make. There's runner. Cool. So what else could I do? I go back to thread 0. We set it. Well, I can GU. We can go up and get out of here. And now the debugger is running. It's running because it's waiting for input. So we mash a button over here that's waiting on GDB. And now we are driving the debugger with that shellcode being read in. Let's go up again from read file. We are inside main. Let's unassemble. What do you think? Let's unassemble runner main. This right here is. This is the call to the shellcode.
Yes.
Right? So let's set a breakpoint there. Get to it. We are there. I'm going to step in. We step in with T because we're tracing this call. All right, let's unassemble at RIP. And we have those few instructions. Hopefully I didn't need nops here. I could have just continued because I had an int3 and I'm a goober. Okay, so we step through there, look at our registers, and I am a liar. Because as Twitch said, so the tab is located at GS0, but part of the tab is a pointer to the tab. And the pointer to the tab is at offset 30. So let's see if we can fix that in our shellcode real quick here. So 0 isn't what I want. You can get this from GS. I think you have to just like move GS 0 and not dereference it. I know you can do it, right? You don't have to do GS 30. Okay, that's going again. Let's attach. The funny thing is I saw that message earlier and I was like, nah, that's Twitch bait. But you really were looking out for me. Okay, we hit our int3 in our shellcode. We step. Where am I? Oh, I'm on thread 0, or thread 1. Thread 0 set. Where am I? I am. Okay, I am where I am. Gosh, dang it. I gotta do this over again. This is why terminal tools are awesome. All right, guys. The clicking. The clicking. Let's select frame 0. Am I where I think I am? Yes. We go there. We go there. We jump out from main. I break at this point here where that call happens. I don't know why the int3 didn't get caught. Okay, continue onward. We're at that call. We go in. We step again. Do we have RAX? Okay, RAX exists. Okay. So, this is what our tab looked like from our happy command, right? My claim is RAX is a tab. Now you can display something as a type with DT. If I DT, I believe it's underscore tab, and then that address. First off, there's a little bit more going on in here. I don't know if I casted the right address right, but I'll tell you that I did, in fact, make a struct. Okay? Just a little bit, guys. Don't worry about it, though. It's implementation specific. So, that is something that is worth being aware of. Now, one of the things inside of the tab is this pointer, which is to the peb. So the tab points to the peb. If I click on that, we now have a peb struct, which if you look at the NSDN peb, you'll find a similar nice, small, compact little thing. As you can see, this clearly is here with the peb. One of the things that's in the peb is this loader guy. Okay? This loader guy keeps track of the modules that are loaded into memory. Remember there's a whole bunch of like hand waving at the beginning. You're like, I don't know, man, there's this NTDLL, there's this kernel stuff, right? They're modules. These are the images that get mapped into memory. Okay, well, that gets tracked, but that happens at a process level, not a thread level. So that information is stored in this peb, which, as we can see, is accessible from user space, right? This isn't a kernel debugger. These three lists, which are list entries, link to the same data, but in a different order or fashion. It's all the modules that are loaded in this thing, right? It's going to be these 5 things or 4 things right here, but linked in different orders. One of the things that's useful is this in order list, which, as you see, we have flink and blink. All right. Now, when I make a linked list, I usually have flink, blink, and thing, right? But there is no thing here in this linked list. So what the heck are we linking? Like if I go to flink and then I go to flink, everything just goes to flink and blink, right? This isn't a particularly useful data structure. Well, it turns out that this whole thing, MSDN peb, from the tab, we could go to the peb, and from the peb, we can find the loader, which is a peb data loader, which means then we can go msdn peb loader data. We get to peb loader data. Okay, this is a list entry. And then it tells us that the thing that is actually being linked here is a loader data table entry. So where's Flink and Blank? Flink and Blank are the list entry of the struct. So as we move through this linked list, we're actually moving at this offset, which we see as pvoid2. So this is 16 bytes into the entity that is being linked. So if I wanted to see these structs,
We go back 16 bytes.
we go back 16 bytes.
Jeez. All right.
Exactly. That's why I needed to, I'll run late until I finish this, right? This is going to be also in the pre-recorded lecture material that's presented a bit more formally. But I wanted to make sure that I hit this today. So let's go back to my loader data. And then we click on the in order module list is the one that we want. So this is my first one, and it's located right here. So what happens if I display this as a type? And what was it? Loader data table entry. Loader data table entry. And I want this minus 16 bytes. Okay? Well, this doesn't mean that it worked, right? Because I could cast anything to any struct. But do the values that we see make sense? Well, this one, not so much. All right, well, let's go to Flink. Okay. Try this one. Because that first one would be the head pointer. Hey!
Okay.
We see kernel 32.
Oh, there's a DLL base there.
And there is this interesting thing that somebody noted. There is a value DLL base. This DLL base, we'll just copy it and show that right there. This is this. So if I have shellcode, I could write shellcode that would load from that offset of the GS, gets me to the tab. From the tab, I could write shellcode that could figure out the offset to the PAB. From the PAB, I could find the offset to the loader. From the loader, I could find the offset to the in-order module list. And from the in-order module list, I could follow Flink a couple times until I get to this, and then I subtract 16, because that makes sense. And then find the offset forward from there, and I could find this value. That tells me where kernel 32 is, and kernel 32 is the module that gives me the Win32 API.
Which is the happy userland thing.
Which is the happy userland thing. But wait, there's more. So, if I have that, that gives me where everything is loaded in memory. It doesn't necessarily tell me where functions are. Right? Now, I will save the long version of this, which makes me sad because the long version is a good time. All right, guys. All of the things that are hiding here. And instead, what I'm going to do is I'm going to open up Windows System 32, kernel 32 DLL, which is that same file. That's the backing file for that kernel 32 module. Right? Somebody says it feels like the vtable exploit again. Yeah, it's almost like we had that module that like navigated structs and things by design so that you learn this skill set. Because those type of problems exist everywhere, right? So this is CFF Explorer, which, as we saw, is installed in the VM here. I don't think I can make this bigger. I might be able to. Okay, I can do this zoom to get you something. It is a PE viewer, right? The beginning of a PE file is actually a DOS header. There's lots of interesting things here.
You'd love to see something called e-magic.
Well, so like one of them that is a trap. All right, this is a tangent. Optional headers. You think they're optional? No. Right? All right. They actually, some of them are required. There are some that can be excluded if I remember right. But generally speaking, there will always be something under optional headers. The thing that is interesting for our context here is the export directory. Okay, so the way that Windows deals with imports and exports is the executable file has an import table. The DLL has an export table. So we're looking at this export table. Now, I'm not going to, in the interest of time, do you guys want to hear the long one, or do you guys want me to just get you out of here?
Probably need to head out soon.
Okay, so in the interest of time, the offset you want is this function RVA value. And so you can't search this, but you can scroll down. And so if I wanted to do write file, I don't know why these tools don't have search, but I also don't know why they aren't terminal tools. Okay. If we were to find, whatever, I wanted to call get module handle A. This offset right here is the offset from the DLL base where the pointer will be stored through the function.
Okay, so we would have to call this as a keyword pointer or whatever.
Yes. So you would take the base address, you would add this offset, and you would move the keyword from there into RAX and then call RAX. This is not the offset to the beginning of the function. This is the offset to where the pointer to the function is.
Okay.
Now, there's a lot more interesting stuff going on in here, but in the interest of time, I won't keep you. This is the end one. Somebody says it's amazing. This is everything you need to know. This is not even 10% of what you need to know about Windows. All right. But this isn't what is absolutely necessary as a bare minimum to solve the challenge. But this was the intended approach, was for you to do some struct navigation, pivot around this stuff, and see how this works. All right. With that, I'm definitely kept everyone late. I appreciate you indulging me, and I will leave you. Goodbye and good luck.